All right, so for all of the algorithms, the timestamps of this video will be located in the description down below. Also in the description, you will find a link to the GitHub repo that contains all of the codes that will be implemented during this video. So first of all, I would like to talk about testing our sorting algorithm implementations. And how to do that is, of course, you can manually create some test cases and you can test them. But for the purpose of this video, what I used is a bash script. And I would like to share, first of all, this thing with you so you can get an idea of how you can automate the process of testing your implementations. So essentially, it's a very simple for loop that I'm using here. And I define these variables from line 2 to 7. So this is just the program. So I just give the name of the program as the first argument to my bash script. And then I define how many tests, the length of the integer arrays, the lowest possible value, and the highest possible value that may appear in the integer array. Then I just create these two files. Okay, I just say touch, input.in and output.out. So input will contain the random integer array and output will contain the sorted integer array. So I'm using random integer array, which is a program that I created in another video. Make sure to check that out. And I give to that program the parameters that we will be using. And the output of this random integer array program will be saved, will be stored in the input.in file. Then I go ahead and I just run my algorithm on that input array, and I output it by redirecting the output to the output.out file. Then I go to my checker here, which is another program I developed. And what this program does is it just reads a sequence of numbers. And as soon as one number is greater than the previous one, it will return number 1 as an output. Otherwise, it will return a 0. So here I'm just checking if the result that I save in this checker variable is greater than 0. So if it is greater than 0, which means that it is equal to 1, I just echo that we have failed, and I know that my sorting algorithm is not correct. And otherwise, I will just output correct. I will delete these files, so the input and the output file. So I clean my directory after testing. And I repeat this for how many tests I have defined here. So I begin from number 1 until the number I have defined. So in this case, 20, I will be running 20 tests from 1 to 20. And I just echo the verdict here. So if the verdict didn't change, I will just output all tests passed. So that's pretty much it for the bash script. So let's move on to the algorithm implementations. All right, so to kick things off, I implemented a header file to make my life easier when implementing these sorting algorithms so that I don't have to worry about inputs and outputs every single time. So let's go through this header file so you can get a basic understanding of what I'm doing here. Here I'm just including the standard C++ libraries. So that covers all of our needs about the data structures that we will be using abstractly in our implementations. Using the standard namespace here, we don't really need any more namespaces. Our code is quite short, so this should be fine. Then I'm using these vector variables here. So input vector and output vector, they contain long integers as their elements. And these are global, so they can be accessed by any function, essentially. Now I define my void here, which I call my sort. So this is where we will be implementing our sorting algorithm, essentially. And then this is the main function, which does the input and output and just calls the my sort here. So here with this while loop, I'm just going until I meet the end of file of the standard input. Then I just read long integers one by one, and I push them back into my input vector, okay? Then I just, after I have run my sort here, which will sort the array essentially, and put it into the output array, the output vector, pardon me, I just go from the first element up until the end, and one by one, I output the elements of the output vector. So that's pretty much it for the header file. All right, so let's begin with counting sort. So counting sort is one of the easiest algorithms to implement, and one of the fastest, actually the fastest that we will be implementing in this video. And that is because of the low complexity it achieves of O n plus m. So n being the number of integers I have in my array, and m being the number of different possible values that each integer might get, okay? So counting sort makes the assumption that we have enough memory to store for all of the possible values a tally of how many times that value appears in my array. So let's go ahead and implement counting sort. So we have one integer array here, which I'm calling apps for appearances. And let's say that my values will be ranging from 0 up until 100,000, okay? So how many memory places I need is 100,001, okay? And then I simply just iterate through my input array. So from the beginning until the end, and I go to my array here, and for the value that I find in index I of my input array, I increment this by 1. I can do this since these are initialized to be all zeros because of me declaring this array to the global scope, right? And now the only thing we need to do is to go through all of the values and just look at the tally for each value and construct the output vector, right? So what we do here is we just have a for loop again. We go from the lowest value, which is 0, up until the highest value, which is 100,000, okay? And we just we have a while loop now, and we take the value that we have found on index I of the appearances array, and we evaluate that. If it's greater than 0, we keep doing the for loop, and then we decrement it. So first I evaluate, then I decrement, right? And after that, I just go to my output vector here, and I just push back by UI, right? So that's pretty much it for counting sort. Now, if you want to keep the same idea that counting sort has, and actually work with a greater range than this range we have here. So let's say that the user needs to have an array which is going from 0 to 10 to the power of 18 to be sorted. So what you can do is, instead of using an array here, you can use a map. Let's say that the keys are long, okay? So 10 to the power of 18 fits into a long integer. And integer will be the number of occurrences that a number might have. We don't need a greater type here, okay? We don't need more than 2 to the power of 32 to, let's assume that it's enough to just have an integer here, okay? So this is the map. And now the only thing I need to change from my implementation is actually, I will be duplicating this for loop here, okay? Let's comment this one out. Okay, and this for loop here will remain the same. But let's go through the complexities at this point so you understand the difference of using a map with using an array. So when we used an array, the complexity we had was O(n) plus k, where n, again, is the number of elements. So this for loop here had a complexity of O(n) linear, since it just went through the elements of the input. And for each one of them, it did one single calculation, right? And the other for loop that we had, it would go through all of the different values. So if k is the size of the range, Then we have k iterations here. So from 0 to 100,000 in this example here that I used. And then for each single value, we just have this while loop, which we know that it will not cost us more than n, because we don't have more than n appearances in an array that has at most n elements, right? So this is the n plus k part of the complexity, right? So now that I'm using a map, I actually have an O n log n complexity. And let me explain why. This for loop here will actually need, will execute n times, right? And for every time it executes, this will not take a constant time anymore. It will actually take a log n time, a logarithmic time, because a map is essentially a tree, and to insert an element to map, you need a logarithmic time, okay? So that's the overhead. This for loop here is the overhead of our implementation using a map. The other part, which is just iterating through the map, is actually taking linear time. So let me implement this and I will show you why. So to iterate through the map, I'm just going to have an iterator to the map that has a long key to integer values. Let's call these IT, okay? And now our for loop, instead of beginning from the first value, it will just begin from the lowest value in my map. And how I do this is I say just it equals to apps, which is the map, dot begin, okay? And then it will not be equal to apps.end. So as long as it is is iterating through the map, right? And then we just increase the iterator by 1 every time. Then we go to the same while loop again. And what we do this time is, instead of using this, we just use the iterator. So we say it, and we need the value, like how many appearances we have here. So we say second. Okay, so this gives us the value, so the second part. And then we use a minus here to decrement by 1. So again, we evaluate first, and then we decrement this value by 1. And what we're gonna put in our output here is it, the first part of the iterator. So that's the key, okay? And that's pretty much it for the implementation using maps. Now, this loop here, why does this loop take a linear time? Is because it's actually traversing the map, which is essentially a tree, and that tree has at most n different nodes, because we have at the most n different values in our integer array. Okay, to traverse a tree, you will need to pass from every single node at the most 2 times. So 2 times n, that gives us O(n), that's linear time. Okay. So that's pretty much it for counting sort. Let's move on to the next algorithm. All right, so let's go ahead and implement bubble sort now. So bubble sort has a very distinct structure. That is, you have a do while or a repeat until in the outside for the outside loop. So let's go ahead and implement that. And in the inside, you need a for loop, okay? Okay, now for the do while loop, we're gonna need a boolean to know when we have to stop. So the boolean, let's call it swap check. Okay, let's set it to be true initially, and as long as this is true, we're gonna keep going. Otherwise, if it becomes false, we're gonna stop. We are setting it to be false every time we enter the do while. Okay. Then another thing we're going to need is an index to the last element of our array. We can get this with the input vector size. We give a -1 so that we are pointing to the last element, okay, here. And now what we do is we are pointing to the second element, so I equals to 1 until I is smaller and equal of last. What we will be doing is we will be incrementing it by 1, okay? Then inside this for loop, you just need a simple if statement. So if the current element to which I'm pointing is smaller than the previous element, I'm just gonna swap them, okay? Because it supersedes this previous element, so it must be greater than it. So if it's not, we just swap. Right. Now, the other thing we need to do is to set this swap check variable to be equal to true, since we have made a swap. And after we're done with this loop, we just decrement by 1, okay? So this is the most naive implementation of bubble sort. The result, by the way, we need to copy it to the output array. So all right, and after we copied it, we have copied it. What we need to do now is to improve this implementation, right? Because it's not the optimal one. Instead of pushing the last element one by one, because okay, bubble sort. What bubble sort says is that after I'm executing this for loop the very first time, and the last element will 100% be the greatest element, because wherever this greatest element exists in this array, we will eventually push it to the back of the array. Okay, with this swap, with this swapping that we are doing on the elements one by one. So that is true, but what is also true is that we, instead of decrementing this one by one, what we could have done is have a variable here. Let's call it new last. Okay, this is gonna be equal to 1. And every time we make a swap, we're gonna update this to be equal to I. Okay, so new last will eventually take the index in which we have done the last swapping, right? And we're gonna set afterwards last to be equal to new last. And that will also sort the array, because after the last time we have done a swap, the subsequent elements did not cause for us to make a swap. So that means that they are sorted, because this was never true. We have never had an element which was smaller than its previous one. So this part of the array is sorted. It's not only sorted relative to itself, but it's also sorted relative to the entire array. So these elements that we have in the back of the array are going to be the greatest, are going to be greater than the elements on the beginning of the array, because they have been swapped to reach their positions, right? So this is the most optimal way you can implement bubble sort. Even with that, bubble sort has a quadratic time. So the complexity of bubble sort is O n squared, where n is the number of elements. And that's pretty much it for bubble sort. Let's move on to the next one. All right, so let's now implement the merge sort. Since my function doesn't have any parameters, I'm just gonna implement another function here. Let's just call it here void merge sort. Okay, and this takes two parameters, left and right. These are the two indexes that point to the leftmost and the rightmost elements of the array or subarray that I'm processing at the current merge sort iteration. Here, I'm just gonna call it with the left index being 0 and the right one being the size of the input vector -1. So that's the rightmost index, so to the rightmost element. I need to define the signature here as well. So this just defines it. And here, I'm just gonna copy to the output array right? So here we can just now begin implementing merge sort. So the first part is to look at the corner case, which is that the left index equals to the right index, which means what? It means that we have only one element in our subarray. So in that case, it is sorted, so we just return. Otherwise, we are going to do the divide part here. And in this divide part, what we do is we have a mid index now, and this mid index equals to left plus right divided by 2, okay? And then we just do the part where we call the two individual subproblems. So here we just say merge sort of left until mid, and merge sort mid plus 1 until right. So here I'm going to have two arrays essentially, from the left until mid, and from mid plus 1 until the right index, okay? After this is done, the only thing left to do is to merge. To do that, we're going to use a vector of long. Let's call it merge vector, MV, okay? And we're going to have two indexes, I and j here, okay? So I is going to equal to the leftmost part of the left array, that is left, and j will be equal to the leftmost part of the right array. So mid plus 1, okay? Now we're going to have a while loop. So as long as these two indexes, either one of them is in the bounds of the arrays, so I smaller or equal to mid, or j is smaller or equal to right, okay? I'm just going to keep repeating this thing here, which is if I is out of bounds, is the first check we're going to make, then we just say mv dot pushback what input j is what we're going to put back, okay? And then we increment j by 1, all right? Then we have an else statement here, else if statement here. So if j is greater than right, which means that j now shows points to an index out of the bounds of the subarray, which is assigned to, we're just going to say mv dot pushback input I plus plus, okay? Otherwise, we're going to compare between the two elements. So essentially, what is the point here? The point is that the leftmost elements, after the subarrays are sorted, are the lowest values of the subarrays, okay? And because the subarrays are sorted, this will always be true, okay? After we have used that lowest element and pushed it into the merge vector here, it will essentially be removed from the subarray logically, and the next element to its right will now be the lowest element of the subarray, right? So what we do here is we have an if statement. If input I, so the element that the left subarray has and point to right now, is smaller than the element of the right subarray, we just say mv the pushback input I. So we get element pointed by index I in this case, and we increase I by 1, okay? Otherwise, we say mv dot pushback input j, and we say j plus plus, right? And that's pretty much it for the merge part. So we merge them into merge vector, and now we just need to copy them into the original array. So we do this with for loop here. So as long as we're smaller than our vector size, we just increase by 1, and we just say that input leftmost index plus k, okay, equals to this new to this new value, which is the merged value, the merged vectors value on index k. So I'm using the left here as the offset on to actually be able to map the correct element to the correct index in which k should be assigned to. Okay, so since I'm processing subarray that begins from left to right, by adding left to k, I make sure that I'm pointing to the correct element, right? So that's pretty much for the implementation of merge sort. So we have explored 3 algorithms, sorting algorithms essentially. One has a complexity of O(n) plus k, where n is the number of elements in our array and k is the size of the range in which they may belong into. And the next one was bubble sort, which has a quadratic time, which is very bad. So it's n squared essentially, O(n) squared. And this is merge sort, which has a time of n log n. It uses element-to-element comparisons. Okay, it doesn't require obscene amounts of memory so that you can keep a tally for every single element. So as you can see here, we essentially, with this if statement is where we compare element by element. Okay, and yeah, so you have 3 different complexities, and all these 3 algorithms are very easy to implement. So I hope you find this video helpful, and these algorithms will prove to be helpful for you in the future. So if you like the video or you would like to see some other sorting algorithm being implemented, leave the video a like, comment in the comment section down below, subscribe to the channel, and I will see you in the next one.